All right, welcome back, everyone. We wanted to go through a couple examples for the equation of planes. We had gone through building the equation of plane. Now some just interesting problems, kind of meshing our equations for lines with equations for planes and so on, and seeing that interaction with these different equations, right? So later we can start to even include discussions about kind of interaction between different types of surfaces and the plane, or even just two different types of surfaces, right? So let's start to go through this discussion, some examples here from 12.5, okay? All right, so as we get started, let me put this heading on. So equations for lines, planes in 3 dimensions, right? We had gone through our different equations for lines, that vector format, that R of t, that vector form, knowing a point on the line and the direction vector that it follows. Then we got into like our parametric form for the lines, as well as symmetric form. And then we dealt with most recently equations for planes, right? As long as we know a point on the plane and a vector normal, perpendicular, orthogonal to that plane, then we can define that plane in 3D space, okay? So now kind of combining that information, let's go through some examples here. So let's check out this problem. Let's try number 46. This is on page 872 of my textbook, right? Still in section 12.5. And we want to find the point at which the line intersects the given plane. Okay. And in this case, we have for our line, the equations here, x equals t minus 1, y equals 1 plus 2t, and z is equal to 3 minus t. Try to get those signs right. And then our plane having that equation, 3x minus y plus 2z is equal to 5. Make sure I copy that down properly. Okay. And so again, before, not necessarily worried about the precise location of this plane and line, okay, but visually kind of inspecting, we have our plane here, right, extending everywhere, that sheet of paper stretching across. Then we're going to have our line cutting through in some way. And so what we want to figure out, where is our point of intersection? Where is that line cutting through that plane? Okay. And so just like when we were intersecting lines back in algebra, right? Figuring, okay, when are we going to intersect? We know that the line and plane are going to intersect at a shared, right, a common x, y, z coordinate, right, ordered triple. Right? They're going to share the same exact x, y, z location for that one point where they intersect. Okay, and again, imagine like kind of having this pen cut through my sheet of paper. It's only going to cut at one particular point and trying to find that location, right? So in that case, it leads us to our process here right? This idea that the x, y, and z values must be the same, must correspond for both line and plane. So that means we can take the expressions for x, y, and z from the line equations, those parametric forms, and substitute in to the plane equation, right? That x, y, and z has to work for both equations, then solve for that parameter t. It tells us exactly what value for t to use to give us that precise point on our line that should correspond to our point on our plane as well. Okay, so kind of going back to it, for our line, oops, sorry about that, dropped my pens. For line, our x was t minus 1 or negative 1 plus t in that more common formal parametric form. This one follows that parametric form. Y sub 0 plus b times t, right? 1 plus 2t. And then the z, 3 minus t. For the plane, 3x minus y plus 2z was equal to 5. So now replacing x, y, and z with our expressions from that line, x was t minus 1. The pieces in here, 3 minus. The y was 1 plus 2t plus 2 times z. And again, z was 3 minus t. That's all supposed to be equal to 5, right? So I'm just replacing, wrong color there, my x, y, and z in my plane equation with the expressions, those parametric forms for my line, because I know those need to coincide, they need to correspond. So that x value needs to work for my plane, the y value needs to work in the plane, the z value needs to work to make that plane equation true. So now getting into solving, right? 3t minus 3 minus 1 minus 2t plus 6 minus 2t is equal to 5. Combining my t terms, my parametric, 3 minus 2t is 1t, 1 minus 2t negative t. Constants here, negative 3 minus 1, negative 4, plus 6, that sounds like a plus 2, is equal to 5. Negative t is equal to 3. So t is equal to negative 3, right? So when t equals negative 3, that point on my line in particular is going to be the point where we're intersecting, where we're passing through the plane. So if I go back into my equation for my line, right, now find the exact point on our line. Rewrite my equations real quick. X is going to be t minus 1, y is 1 plus 2 times t, z is equal to 3 minus t. Plug in our value for t is negative 3. That's going to lead us to our point. X equals negative 4, y equals, and z equals, my placeholder's up, 1 plus 2 times negative 3, negative 6, 1 minus 6, -5. 3 minus the -3, 3 plus 3 is +6, right? So this leads us to our point of intersection. This is just a single point that's going to be both on our line and on that plane. We can go back to verify that this ordered triple, this point, does indeed satisfy that equation for our plane, right? It's on our plane, so there's our point of intersection. Right, and so that's just that use, that kind of slow progression into identifying that if we're trying to figure out where these different surfaces, these different items, these graphs in 3 dimensions work, where they're going to intersect, what points they share in common, right? Using the effect of intersection that the X, Y, and Z have to all correspond, we can use that substitution to locate those types of points, okay? Very good. Okay. So this next one, the next example I wanted to go through takes a little bit of thought in considering. I think the process once we get there won't be too horrible, but that initial kind of setup might take some time to think about. So let's check out this next example, problem number 60. That same page, page 872 from section 12.5. And it wants to find the equation, okay, for the line of intersection of these 2 planes, of the planes. Okay, and so now we start to work on this, kind of imagining. We have our first plane, and I'll have to write these equations out in just a second, but just visualizing. We have our first plane, this sheet of paper again, then another plane, kind of arcing down, where these 2 planes, where these sheets of paper cross, we're going to get this line of intersection, right? It extends infinitely, but just in that visualization, having these 2 kind of sheets of paper intersect, okay, and figuring out where they do intersect, and that line that they form is going to be our question, right? So again, kind of stealing the little graph I had from last time. But if we have these 2 planes coming in, try to get that to match up, and intersecting, right? What is that line across which they're going to intersect? Right, so kind of like what we need, if you imagine this then, kind of using that to my benefit, if I have that point where the planes intersect first, then I have the direction along which that line is going to move, I can build that equation, okay, for that line. But exactly that, we need a point where these 2 planes are going to meet. We kind of did that with our equation, or in the previous example, right, finding that point of intersection between a line and a plane. So now we need to find another point of intersection. But now we're also having to discuss these kind of direction vectors, right? What direction is that line moving to kind of identify that line of intersection? All right, so let's start to think about that. Let's take some time here to address. All right. Okay, so let's label, let's think about what we're going to need. So to get that line of intersection, that's our goal. We will need, of course, we'll need the equation of those planes as well. I'll write that up, okay? But what we're going to need, we'll need at least 1 point where the planes intersect, right? 1 point that they share, and we're also going to need the direction vector for that line of intersection. Right? So as long as we can find that point of intersection and this direction vector that that line follows, whether it be this direction or the other direction, right? It'll just be the same quantities, it's negative. Then we can build up that equation for our line. Okay? All right, so let's start to think about this though. Let's go through this first part. In plane number 1, my equation is z equals 2x minus y minus 5. In plane number 2, z is equal to 4x plus 3y minus 5 as well. Okay. So this is our particular information for that problem. So trying to find this line of intersection for these two planes that will indeed intersect. Okay. And so again, since these planes, we can imagine kind of expand out everywhere. Okay. What we can do is that the following, so to find a point of intersection, we can first pick an arbitrary, right, just some random value, okay, value for either x, y, z that they will share in common. Right, and again, as long as these aren't just kind of those level planes sitting at exactly z is equal to 5 all the time, or c is equal to 3, or x is always equal to 1, whatever it might be, right? When we start to see that our normal vectors, and we can rewrite this if you wish, 2x minus y minus z is equal to positive 5, and this one, 4x plus 3y minus z is equal to positive 5. Just rearranging it a little bit, all right? Think about our normal vectors, what direction they're facing at some angle, right? At some point, it's going to have to pass through any x, y, or z, unless they're like those level planes that are fixed at a particular z that aren't going to tilt at all, right? Or if we have an x or y that's fixed, that is not going to deviate, then pretty much, since these are infinite expansive surfaces, any x, y, and z has to occur at some stage, at some point along that plane, okay? And so we're just going to arbitrarily pick one value. So in this case, let's let z equal to 0 out of ease. Figure out where these two planes cross when z equals 0, the xy plane, okay? So that means that plane 1, 2x minus y minus z is equal to 5. If z is equal to 0, that means 2x minus y is equal to 5. And then the second plane, 4x plus 3y minus z is equal to 5. All right, so in particular, when z equals 0, we could do the same thing with z equals 1, z equals 2, 3, negative 3, whatever you want to choose, just some arbitrary value. We get this new system, right? So now they already have the z in common. So now solving here, taking this first equation, we can multiply by 3, for instance. (6x minus 3y is equal to 15). Second equation, 4x plus 3y is equal to 5. Adding down, 10x is equal to 20, or here x equals 2. And when x equals 2, what does y have to be equal to? Going down, y is going to be equal to -1, which you verify. Right, by solving that system, this gives us our point, or a point of intersection. Okay. So with that process, a point of intersection then, and depending on which value you may choose to keep fixed, right, whether you choose z equals 1 or even x equals 0, whatever you want to do, right, a point of intersection that we can use, 2, -1, 0. Right, that's like our p sub 0, our initial point. Okay, let me slide this down real quick. I know I'm jumping around a little bit in my paper. All right, but we've just found a point of intersection. Now we need our vector, our direction vector. And that came from choosing a point, value, arbitrarily for any of those variables z equals 0 out of ease, out of common practice. Okay, what we'll see. Then we'll find the corresponding x and y values. So this point 2, -1, 0 is part of both of our original planes. So we have a point where these two planes intersect. Now we need that direction vector. Okay, so now we're going. So for our first plane, our equation was, let me copy that down again real quick. In that rearranged form, 2x minus y minus z is equal to 5. The second plane, 4x minus or plus 3y minus z is equal to 5. So that means that my first normal vector, right, that vector normal to that plane, 2, -1, -1. My other normal vector, and 2, 4, 3, -1. Right? And so now that property that any vector in the plane, whether it be in plane 1 or plane 2, right, will be perpendicular or orthogonal to the normal vector. Right? So when we start to consider, here's our first plane. There's my normal vector. Any vector that's in that plane should be perpendicular to the normal vector. Right? Any direction we go, that normal vector pointing out from it is going to be perpendicular. And so even when we look at this other plane, right, it's going to have its normal vector. The same thing, any vector in that plane, right, I'm imagining extending from that point of intersection, is also going to have to be perpendicular to that normal vector. So in this case, So our direction vector for our line since it's this line that's in both planes, will be orthogonal, will be perpendicular to both the normal vector n1 and the normal vector from our second plane n2. So if we're perpendicular orthogonal to both of those normal vectors, sounds like we need the cross product, right? So incorporating the tools that we've learned in this chapter, when we look at the cross product between our two normal vectors, right? Normal vector 1, 2, -1, -1. Cross that with normal vector 2, 4, 3, -1. Okay. Doing that cross product, when you start to see that expansion, that 3 by 3 determinant, jumping ahead a little bit, but going through that 3 by 3 determinant, crossing out that column, that row, doing our minor, we're going to calculate, we're going to compute here, 1 minus -3, which is 1 plus 3, minus, and now for the j, cross out that column, that row, we're going to get here 2 times -1, -2, minus a -4, so plus 4. And then lastly, for that k component, column and row go away. 2 times 3 is 6, minus 4 times -4, so 6 plus 4. So in this case, we're getting 4i, -2 plus 4 is +2, minus stays minus 2j, plus 10k. So we could keep that direction vector for our line V as that 4, -2, 10, or even scaling it down, divide everything by 2, 2, -1, 5. It's still going the same direction, it's just a smaller, shorter in magnitude vector, right? You can even make it a unit vector if you so desired, right? And depending on which vector you put first or second here, we might get similar constants, but opposite signs, -4, +2, -10. It's just going that opposite negative direction, if you will. But now we have our direction vector. We found our point. That's all we need. So now for our equation, whether we do the symmetric equations, parametric equations, we're on our way. All right, so our equation for the line of intersection then, right, our initial point, 2, -1, 0. Our direction vector, that A, B, C, 2, -1, 5, we obtained from that cross product. So in our parametric form, x is going to be equal to x naught plus a t. Y is going to be y naught plus bt, so we'll go -1 t. And then z naught plus c t, so 5t there. We can put this form. Or in symmetric equations, right, x minus 2, right, x minus x naught over direction number 2. Y minus y naught, y minus -1, y plus 1 over -1. Z minus z naught, so z minus 0 is just z over stretch number 5. There we go. So it'll be this parametric form, symmetric equations for that line of intersection for those two planes. Okay? And so something not touched upon in my discussion, but just as we looked for that cross product of our two normal vectors to get this vector orthogonal perpendicular to the original two, just like we did our dot product, we want to find the angle between these two vectors or between those two planes. You can use the angle between your two normal vectors with that dot product. We can do that similar kind of work there. I know I didn't address it in this particular set of examples, but going back into some of those different types of applications and equations and calculations we had done before, we can apply it now with our normal vectors of planes to see similar concepts, okay? But in this example, wanting to get that line of the intersection for these two planes, finding our first point, letting z be 0. You could have done the same thing with y equals 0 or x equals 0 or any other value for that matter. To get a point, the direction vector, since it has to be perpendicular to both normal vectors of the planes, we use that cross product, and then we build our equations from there. All right, so I'll leave it at that for today. Questions, concerns, please email me, let me know. Otherwise, office hours on our Canvas page, you can join in and ask questions there as well. All right, take care. See you all soon.